The topic of my presentation is Design, Simulation and Analysis of an OFDM Communication System. I'll start by introducing the OFDM, what it means, the OFDM communication system, how it works, and how we use the inverse fast Fourier transform for the OFDM signal generations. Then I'll talk about the advantages and disadvantages of OFDM. Then I'll discuss about the problem which I'm dealing in my paper of PAPR. I'll show some MATLAB simulations of the OFDM transmitter and the PAPR, and then finally giving my conclusion. So what is OFDM? OFDM is the orthogonal frequency division multiplexing. It is a multiple carrier system which splits the high rate data stream into a number of lower rate streams that are transmitted simultaneously over n subcarriers. So basically, OFDM is a special case of FDM where the subcarriers are orthogonal to each other. In OFDM, the total signal bandwidth is divided into n overlapping frequency subchannels. Each subchannel is modulated on a separate symbol and then n subchannels are frequency multiplexed. So, if there is some interference or fading in the OFDM multi-carrier system, only a small percentage of subcarriers are affected instead of the entire link going down in single carrier systems. So the main concept of the OFDM is orthogonality. The two symbols are said to be orthogonal if their dot product is 0. In other words, it means that the signals are separated by 90-degree. So here we can see this blue one is one OFDM. It represents one OFDM symbol, and these are 4 subcarriers. Basically, it shows 4 subcarriers in one OFDM symbol in time domain. And similarly, we can show the spectra of individual carriers in the frequency domain. So the main concept in OFDM is, as I said, it's orthogonality. So in OFDM, the sidebands of the individual carriers overlap, but the signals can still be received without adjacent carrier interference. So let's talk about the OFDM communication system. This is a block diagram of the basic OFDM system. Here our data is given as an input to the serial to parallel output block, and we can see the output of the serial to parallel converter is given to the symbol mapper. In symbol mapper, the symbol mapping is done based on the constellation diagram of our modulation technique. Here I'm using QAM, so here the symbol mapping is done as per the QAM constellation diagram. The output is then fed to the IFFT, which is the inverse fast Fourier transform. It is the most important module of the OFDM system. The inverse FFT converts the frequency domain spectrum to the discrete time domain by multiplying it over a range of sinusoids. This time domain signal is now converted to digital to analog converter and goes through the cyclic extension. Here the cyclic prefix is added to remove the intersymbol interference which can be caused by multipart delay spread over the channel. The signal is now transmitted over the channel and it's received on the receiver side. In the receiver side, all the steps that we did in all the blocks that we had in the transmitter sides are in the opposite order. So first the symbol goes from the analog to digital converter where it's digitally converted and the cyclic prefix is removed over here. Then it passes to the serial to parallel converter and then FFT. Now this FFT converts the signal back to the frequency domain which was converted in the IFFT. Going from the demodulator, QAM demodulator and the symbol demapping, it passes to parallel input and serial output converter. Here the data is loaded parallel into the shift register and then shifted bit by bit. So at the output, we get the exact input signal that we were supposed to transmit. So this presentation slide shows the generation of the OFDM signal. As I talked, that the IFFT is the most important block. So what it does is it basically converts our frequency domain at the transmitter side. It converts the signal from frequency domain to the time domain by adding a number of sinusoids over multiple frequencies. And at the receiver side, the FFT converts the time domain into the frequency domain by multiplying it over the range of frequencies. As I said, the OFDM systems are implemented using a combination of fast Fourier transforms and inverse fast Fourier transform blocks. Serial to parallel conversion is done at the transmission IFFT block, and PISO is done at the receiver FFT block. Basically, IFT block provides a simple way to modulate data onto n orthogonal subcarriers. Now let's talk about the advantages of OFDM. OFDM has a multipath delay spread tolerance. Delay spread is a measure of multipath richness in a communication channel. Typically, the received radio signal from a transmitter consists of direct signal plus the reflected signal. The reflected signal gets delayed due to the extra path length, giving rise to different arrival times, spreading the received energy in time. Here we can see that. So delay spread is the time spread between the arrival of the first and the last significant multipath signal seen by the receiver. This delayed multipath spread leads to the ISI, intersymbol interference, which can be removed by adding a cyclic prefix to the multiple OFDM carriers at the transmitter side. In cyclic prefix, a copy of the last part of the OFDM is attached to the front of itself. So a copy of the last part is attached to the front of the same signal. Our OFDM signals have immunity, they are immune to frequency selective fading channels. Fading is a big problem for signals, especially when the link path is changing due to the continuous movement of the mobile users. The faded signals add up to the main signal and degrade its gain. So if the bandwidth of the transmitted signal has a greater bandwidth over which the frequency response virals channel, then it has a constant gain and linear phase, then it undergoes frequency selective fading. If the delay spread is more than one symbol, then the channel undergoes frequency selective fading. OFDM, the advantage of OFDM is that it, like we can see here, the number of the OFDM spectrum is laid on the frequency response of the channels. All the subcarriers are perfectly okay with just two of these. Only two of these are being effective. So instead of losing the whole symbol, we just lost a few bits, which can be then recovered using multiple coding techniques. Another advantage of OFDM is bandwidth efficiency. By using the orthogonal subcarriers, OFDM allows overlapping of the subcarriers without having ICI, and almost 50% of the bandwidth is saved compared to the traditional FDM, which uses non-overlapping subcarriers and needs guard bands to avoid ISI. Other advantages of OFDM includes high transmission bit rates, efficient modulation and demodulation techniques, easy channel equalization, and it supports several multiple access schemes like TDMA, FDMA. Now, there are a number of disadvantages of OFDM. First is the high peak to average power problems. It is also very vulnerable to synchronization errors. OFDM is sensitive to carrier frequency offset due to DFT leakage. High power transmitter amplifiers require high linearization, and hence it's vulnerable to phase noise issues in local oscillators. The problem which I'm working on my project is peak to average power ratio. OFDM signals have a large peak to average uh, peak to average ratio PAPR. It is the reason um, that it has a high PAPR is due to it's because in time domain a multi-carrier signal is the sum of many narrowband signals. So at some in time instances, this sum is large, and at other times it's small, which means that the peak value of the signal is substantially larger than the average value. We can see this in this figure as well, that the peak value is substantially larger than our average value. So basically the PAPR, high PAPR, it strains the analog circuitry. It's a big concern in the uplinking since the efficiency of the power amplifier is very critical due to the limited battery power of a mobile terminal. The dynamic linearity arising from the analog circuits in PAPR results in expensive devices. Also, due to the high linearity, there is a high DC power consumption, which again is not good for our system. So, how can we solve this problem? The simplest and the most widely used technique is the clipping, which is the clipping the parts of the signals that are outside the allowed region. Using high power amplifiers with saturation level below the signal span will automatically cause the signal to be clipped. Filtering can reduce out of band radiation after clipping. So to reduce peak regrowth, a repeated clipping and filtering operation can be used to obtain a desirable PAPR at a cost of computational complexity increase. Selective mapping is another technique where data is multiplied with a set of codes. IIFT is done and the one with the least PAPR is picked. Now, this is the block diagram of the generation of the OFDM symbol. I'll be showing you the MATLAB simulation, but I'm using this MATLAB block diagram for the simulation. Now let's go to the MATLAB. So first we have to consider that in this diagram, first we have to consider that a simulation period T defined as the elementary period for a baseband signal. But since we are simulating a passband signal, we have to relate it to a time period 1 by Rs that considers at least twice the carrier frequency. Therefore, we use it for integer relation Rs is equal to 40 by T. We use a carrier frequency which is close to 90 megahertz, which is in the range of VHF channels. Now I'll run my code, MATLAB code. Now, this is the figure 1 and figure 2. Now, these are the two figures of the OFDM transmitter code that I just ran. In figure 1 and 2, we can observe the result of the operation that we just did, and the signal carrier uses T by 2 as its time period. We can also notice that the carrier is the discrete time baseband signal. We could use this signal in the baseband discrete time domain simulations, but as we should recall that OFDM drawbacks, one of the OFDM drawbacks, they occur in the continuous time domain. So the first step is to produce a continuous time signal by applying a transmit filter GT to the complex signal carriers. The impulse response of the pulse or the pulse shape of the filter input GT is it can be seen as here. We can see the pulse response of the filter input GT. Now, this plot shows the output of the transmit filter in the time domain, and in the frequency domain, this is the output of the transmit filter in the frequency domain. This is periodic as required of the frequency response of a discrete time system. So now I'll start with the I'll go move on to the MATLAB simulation of the to investigate the effect of the PAPR on OFDM signal and the clipping effect. Now I'll run this code.